Imagine for a moment you're relying on an AI for truly important information, maybe a doctor asking it for a critical diagnosis.
Right. High state stuff.
Or maybe you're just looking for reliable info online and the AI confidently tells you something completely wrong.
Yeah.
Or worse, maybe it's making an educated guess, but it sounds absolutely certain. That's kind of the unsettling reality we often face with today's large language models, LLMs.
Yeah, it's a really fundamental challenge if we want to integrate AI into critical applications. I mean, these models have made incredible strides,
Absolutely.
especially with their ability to think out loud or generate those,
Mhm.
reasoning chains. But their internal confidence isn't always reliable.
Right.
They might generate factually incorrect information, what we often call hallucination,
Yeah, hallucinations.
but still deliver it with this air of complete authority. And that really undermines the trustworthiness we need.
Exactly. And that critical gap is precisely why today we're taking a deep dive into something absolutely crucial for the future of AI, their confidence.
Mhm.
Specifically, we're diving into this paradox. Why models trained to think out loud can actually become more overconfident and, well, hallucinate more.
It seems counterintuitive, doesn't it?
It really does.
Okay.
So our mission in this deep dive is to unpack some groundbreaking new research from MIT. They're proposing this ingenious approach called RLCR, that's reinforcement learning with calibration rewards.
Or LCR, right.
And it's designed to make LLMs not just accurate, but also genuinely aware of their own uncertainty and, crucially, communicate it reliably.
So knowing when they don't know.
Exactly. We'll explore the problem, the brilliant solution they've come up with, and some surprising results that could make AI far more trustworthy.
And we're drawing directly from a recent paper. It's titled Beyond Binary Rewards, Training LMs to Reason About Their Uncertainty. It's from Met, as you said.
Yep.
And this research is, I think, a fantastic example of pushing the boundaries, moving us closer to AI systems that are truly intelligent but also accountable.
Yeah. And this deep dive is custom tailored for you, our curious listeners, to cut through the jargon and really get to the core insights quickly and thoroughly.
Let's dig in.
Okay, so we've got this problem, overconfidence. But before we jump into the solution, RLCR, what exactly is causing it in these models that think out loud? I thought generating those reasoning chains, solving things step by step, was supposed to make them better, more reliable.
Well, what's fascinating here is how they're typically trained. The standard approach, often called reinforcement learning with verifiable rewards, or RLVR,
RLVR, got it.
it uses a very, very simple reward system. It's basically binary.
Binary, so just yes or no.
Pretty much. A model gets a reward, say a 1, if its final output matches the correct answer, the ground truth, and it gets 0 if it doesn't. Simple as that.
Okay, sounds straightforward, but I sense a but coming.
There is definitely a but. That simple binary reward, it has a really critical limitation. Think about it.
Okay.
It treats a confidently correct answer exactly the same as a lucky guess.
Ah, right. Both just get a 1. Doesn't matter how the model got there.
Precisely. And on the flip side, it penalizes incorrect answers and complete abstentions. Like if the model says, I don't know, identically, both get a 0.
So there's no incentive to be cautious or to admit uncertainty.
Exactly. What happens is this inadvertently incentivizes overconfident guessing. The model isn't rewarded for knowing how confident it should be, just for hitting the right answer eventually.
And that, of course, undermines trustworthiness if it's just guessing but sounding sure.
Indeed. And there's empirical evidence for this too. Studies have consistently shown that LLMs, even if they start out reasonably well calibrated,
Meaning their confidence kind of matches their accuracy.
yeah, roughly, even those models tend to become overconfident after this kind of standard RL training. And specifically, these reasoning models often show worsened calibration and increased hallucination rates when they're only trained with these simple correctness signals.
Wow. So trying to make them reason better might actually make them less reliable in terms of confidence.
In some ways, yes, if you only use that binary reward.
And that's where the real-world stakes come crashing in, isn't it?
Absolutely.
In fields like healthcare, law, where an AI's output could have huge consequences.
Profound consequences.
These models must not only be accurate, but they also have to communicate uncertainty when it's appropriate. You absolutely need to know if the AI is, say, 99% sure or just 50% sure.
It's a massive difference in how you'd use that information, right?
Totally.
Yeah.
You wouldn't bet the farm on a 50% guess presented as fact.
Absolutely not. So this is the core problem, the crux of the issue the MIT researchers set out to solve. If the model is uncertain, it needs to convey that uncertainty rather than just confidently asserting something that might be wrong.
Okay, which brings us neatly to RLCR. The proposed solution for calibrated confidence, the paper really focuses on two key research questions, as I understand it.
That's right.
First, can these reasoning models be optimized for both things at once, correctness and calibration?
Yeah, can you have your cake and eat it too, essentially?
Right. And second, can the actual content of those reasoning chains, that step-by-step thinking process, can that actually improve the calibration itself? Does the thinking help it know its own limits?
Good questions. And to tackle them, the researchers look towards statistical decision theory, specifically this concept of proper scoring rules.
Proper scoring rules. Sounds technical, but what's the basic idea?
The intuition is actually quite elegant. These rules are designed specifically to reward a predictor, in this case, the LLM the most, when its stated confidence genuinely matches the true probability of its output being correct.
So it's about rewarding honesty about your beliefs.
Exactly. It's not just about being accurate in the end. It's about being honest about how likely you think you are to be accurate along the way.
Okay, this proper scoring rules idea feels key. Can you give us an example? How does it actually work in practice? How do you measure if a model is being honest like that?
Sure. A classic example, and the one used in the paper, is the Breyer score.
Breyer score, okay.
Intuitively, think of it like this. It penalizes the model based on how far its confidence estimate is from the actual outcome.
How far off it is?
Yeah. So imagine the model says it's 70% confident the answer is A. If A turns out to be correct, which is like an outcome of 1, it gets penalized a certain amount based on that 70% estimate. If A is wrong, an outcome of 0, it gets penalized differently, again, based on that 70%.
So it gets dinged more if it's confidently wrong.
Precisely. And also if it's correct but express very low confidence. The score is minimized, meaning the reward is maximized when the stated confidence perfectly matches the true probability.
So if it says it's 70% sure, ideally it should be right exactly 70% of the time when it says that.
That's the goal. It pushes the model to become a truly reliable forecaster of its own accuracy, not just an answer machine.
Okay, that makes sense. So the Breyer score keeps the model honest. That's pretty brilliant. So RLCR, this new approach, it modifies the reward function, right?
Exactly. Instead of just that binary 0 or 1 for correctness.
Which we know is problematic.
Right. RLCR combines the correctness reward with this Breyer score.
Okay, so what does that look like? The formula in the paper is RRLCR is R correctness plus R Breyer.
Yeah, essentially it's 1 II, Q1I. Let's break that down.
Please do.
The first part, 1 II, is just the old binary reward. 1 if the answer I matches the true answer Y, 0 otherwise.
Simple correctness.
Right. But then you subtract the Breyer score part, Q1II. Here, Q is the model's stated confidence. So you're penalizing the squared difference between the confidence Q and the actual outcome. 1 if correct, 0 if wrong.
Uh-huh. So you get points for being right, but you lose points based on how inaccurate your confidence Q was.
Exactly. It incentivizes correctness, and it penalizes the model for being, say, highly confident when it's wrong, or having low confidence when it's actually right. It has to get both parts right.
That seems much more nuanced.
It is. And what's really powerful here, the researchers provably demonstrated this isn't just a clever trick.
Right.
RLCR, using this combined reward, mathematically incentivizes both accuracy and calibration.
Provably. So it's not just hoping it works.
No, there's a theoretical guarantee. It encourages the model to output the most likely correct answer and provide a calibrated estimate of its probability of success.
That's a strong claim. How does that compare to other methods?
Well, they contrast it with things like standard log likelihood loss, which is common in training. Surprisingly, those methods don't always guarantee this calibration property. Sometimes they can even incentivize incorrect answers under certain conditions.
Wow. So RLCR is actually designed for honest confidence from the ground up.
That's the idea. The paper even have a figure 2, that visualizes this really well.
Right, I saw that. What does it show?
It shows how the reward landscape changes. For RLVR, the reward is just a flat line at 0 or 1 depending on correctness. It doesn't care about confidence Q.
Just right or wrong?
But for RLCR, the reward is this smooth curve. It peaks when the confidence Q matches the outcome, high Q if correct, low Q if incorrect. It actively encourages the model to find that sweet spot of accurate confidence.
So it nudges the model towards fine-tuning its confidence estimates, pushing it towards true calibration. That's a fundamental shift.
It really is. It's changing what we ask the model to optimize for.
Okay, theory is great, guarantees are great. But how did RLCR actually perform in action? Let's get into the experiment.
Right, the proof is in the pudding. The researchers set up some pretty rigorous tests.
What did they compare?
They evaluated several methods. There was the base pre-trained model, just as a starting point, then standard RLVR, the binary reward method,
Hmm.
and RLCR, of course. They also included some other baselines, like classifier-based approaches that try to predict confidence after the fact.
Okay. And how did they measure success? What metrics?
They used a standard suite, accuracy, obviously, then things like AUROC.
Area under the curve, right. Measures discrimination.
Exactly. And importantly, the Breyer score itself, since that's what RLCR optimizes, and expected calibration error, or ECE, which is a really common way to directly measure calibration quality.
ECE. Low is better for that one.
Yep. Lower ECE means your confidence is better aligned with your actual accuracy. They used a Quen 2.57b model as their base
Okay. Decent sized model.
and trained it on specific data sets, like HotPot QA modified for question answering and Big Math for mathematical reasoning problems.
Got it. So first up, in-domain performance. How did it do on HotPot QA, the data set it was trained on?
The results here were really compelling. First off, accuracy. RLCR essentially matched the task accuracy of RLVR.
Matched it, so no drop in performance.
Pretty much. RLVR got around 63.0% accuracy. RLCR got 62.1% on HotPot QA, which is key. It shows that adding this calibration objective didn't really hurt the model's ability to just get the right answer.
That's important. You don't want to trade off accuracy for calibration if you can avoid it.
Definitely not. But the real breakthrough, as you might expect, was in calibration.
Okay, this is where RLCR should shine.
And it absolutely did. On these in-domain problems, RLCR substantially improved calibration. Get this. The expected calibration error, EAG, on HotPot QA was reduced from 0.37 for RLVR.
Which sounds pretty high, pretty poorly calibrated.
Very poorly calibrated, yes. Down to a remarkable 0.03 for RLCR.
Wow, 0.37 down to 0.03. That's huge. What does that mean intuitively again, ECE?
It basically measures, on average, how far off the model's confidence is from its actual correctness rate. If a model says it's 80% confident about a bunch of answers, you want it to be correct on about 80% of those. ECE measures the average gap across all confidence levels, so 0.03 is incredibly close to perfect calibration.
So the RLCR model is just much, much better at knowing how likely it is to be right on the stuff it was trained on.
Massively better. And crucially, the base model and the standard RLVR model remained, quote, highly overconfident and poorly calibrated. Their ECE stayed high.
So standard training makes them overconfident, RLCR fixes it. What about other ways to estimate confidence?
Yeah, they looked at a baseline called answer probability, trying to use the model's internal probabilities for the answer tokens. That also performed poorly on calibration.
Why is that? Seems intuitive.
It seems the models just become overconfident about their own generated answers, even if those internal probabilities look good. They trust themselves too much, basically.
Okay. So RLCR's explicit calibration reward is really necessary. Did they see this improvement happening during training?
Yes, they did. They showed in Figure 3a that both the correctness reward and the calibration reward for RLCR smoothly improved together during training.
So it was learning both things simultaneously.
Correct. And interestingly, Figure 3b showed that RLCR's completion lengths, how long its reasoning chains, were tended to increase during training.
What does that suggest?
It suggests the model might actually be developing more sophisticated reasoning about its uncertainty. It's writing more, perhaps thinking more deeply about why it's uncertain.
That's fascinating. It's not just getting better at guessing, it's maybe getting better at thinking about its guesses.
That seems to be the implication.
Okay, in-domain is impressive. But the killer test is always generalization, right? Real-world use means encountering new things.
Absolute critical. Can it transfer this self-awareness to totally new topics or different types of questions?
How do they test that?
They tested the models on 6 diverse out-of-distribution, or OD datasets. Things like Trivia QA, Simple QA, different math datasets, even GPQA, which has graduate-level questions.
A real gauntlet. So how did RLVR, the standard method, fare ODE?
And here's where RLVR really hit a major pitfall. The standard RL training on HotPot QA, it did not enhance the model's reasoning accuracy on these OD tasks compared to the base model.
So no generalization benefit for accuracy.
Nope. And worse, RLVR actually hurt calibration relative to the base model on these OD tasks.
Hurt it. So it made it less calibrated on new stuff.
Yes. For example, the base model's ODCE was around 0.4. RLVR's ECE actually rose to 0.46. It became more poorly calibrated out of distribution.
Wow. That's a significant drawback. Optimizing for confidence only on the training data can actually make it less reliable overall. That feels really counterintuitive.
It really does. It suggests the model might be learning brittle, overconfident patterns specific to the training data that don't hold up elsewhere.
Okay, so how did RLCR do in contrast? Did it manage to generalize its calibration?
This is where RLCR truly triumphed. In stark contrast to RLVR, RLCR achieved substantial gains over all the baselines in out-of-domain calibration,
Substantial gains, while maintaining accuracy.
while maintaining, or in some cases slightly improving, ode accuracy, yes. RLCR's ode ECE was around 0.21.
0.21 compared to RLVR's 0.46.
Exactly. Significantly better calibration on unseen tasks, even compared to the base model's 0.40.
That's huge. So RLCR learns calibration in a way that actually transfers.
It seems so. And the paper's figure 1 visually reinforces this. You see RLVR kind of stuck or even going backwards on ode calibration, while RLCR shows this clear trajectory toward both better accuracy and much better calibration, especially out of domain.
So why? Why does RLCR generalize calibration so much better when RLVR fails? What are the researchers' hypotheses?
They suggest a few potential reasons. First, maybe the very act of reasoning about uncertainty, which RLCR encourages, forces the model to learn more generalizable principles of self-assessment.
Like learning how to be uncertain, not just what to be uncertain about.
Kind of, yeah. Second, the dynamic nature of reinforcement learning itself might play a role. As the model gets better, the RL process constantly pushes it to adapt, which might foster more robust learning.
Continuous adaptation.
And third, they suggest there might be shared internal representations within the model that are used for both generating the solution and for calibrating its confidence. RLCR might be better at tuning these shared parts in a way that benefits both tasks and generalizes better.
So it's potentially teaching the model how to be uncertain in new situations by forcing it to reason about uncertainty explicitly and tuning shared mechanisms. That's quite compelling.
It provides a plausible explanation for the strong ode results, definitely.
And what about the math-specific results? Math seems like a place where precise confidence is super important, but also really hard for LLMs.
Right. On the math benchmarks, the good news was that all the RL methods, including RLVR and RLCR, improved accuracy over the base model. So RL helps with math reasoning.
Okay, that's good.
Now, they also tested a variant called SFT plus RLCR. That's where they first fine-tune the model with supervised examples that include uncertainty analyses and then apply RLCR.
So give it examples first, then reinforce it. How did that do?
Interestingly, SFT plus RLCR achieved the best calibration in domain on the math tasks.
The best. Even better than regular RLCR.
Yes. But, and this is significant, but it came at a cost. It had reduced generalization accuracy on the out-of-domain tasks.
Ah, the trade-off again. Why would that happen?
They suggest it might be due to catastrophic forgetting. The initial supervised fine-tuning might specialize the model too much, making it less adaptable when it sees new types of problems during RL, hurting its ode accuracy.
So maybe too much pre-training on specific examples makes it brittle.
Potentially. It suggests that RLCR on its own, without the SFT step, offers a perhaps better practical trade-off. You go competitive OD accuracy and significantly improved calibration, even if the in-domain calibration isn't quite as perfect as SFT plus RLCR.
That makes sense. Find the balance.
Hmm.
Did the SFT plus RLCR model show anything interesting about the reasoning itself?
Yeah, there was a neat example where the SFT plus RLCR model produced more specific, detailed uncertainty analysis in its reasoning chain compared to the vanilla RLCR model. It really underscored how refining the reasoning process itself can lead to more nuanced uncertainty expression.
Okay, so RLCR training improves calibration, especially ODE, but it's not just about the training, right? The paper also talks about using this new capability after training.
Absolutely. One of the really cool things is that RLCR gives you these explicit, verbalized confidence scores alongside the answers, and you can leverage those at test time to boost performance even further.
How so? What can you do with those confidence scores?
Well, the paper explores two main strategies, and what's great is they don't need any extra models or supervision. It's all baked into the RLCR model.
Okay, what are they?
First is max confidence. If you generate multiple possible answers or reasoning chains for the same question, you just pick the one the model assigned the highest verbalized confidence to.
Simple enough. Pick the most confident one. What's the second?
Confidence-weighted majority vote.
Yeah.
This is a bit more sophisticated. Again, you generate multiple responses. But instead of just taking a simple majority vote, you weight each answer's vote by the confidence score the model gave it.
Ah, so more confident answers count more towards the final consensus.
Exactly. It uses the model's own self-assessment to improve the aggregation.
And did these strategies actually work? Did they improve accuracy?
Yes, they did. They showed in Figure 4a that accuracy generally improves for all methods as you generate more samples or candidates, which makes sense. More chances to get it right.
Standard ensembling benefit.
Right. But the confidence-weighted majority vote consistently outperformed both the vanilla majority vote, just counting votes equally, and the max confidence strategy.
So using those RLCR confidence weights really helps squeeze out more accuracy.
It definitely does. It shows the confidence scores aren't just for show, they contain useful signal.
What else can you do with the confidence scores?
Another neat trick is ensembling the confidence estimates themselves.
How does that work?
You take one fixed answer, maybe the one chosen by majority vote, but then you generate multiple different uncertainty analysis chains for that specific answer.
Okay, so multiple takes on why it might be right or wrong and how confident it is.
Exactly. And then you just average the confidence scores from all those different analyses.
And that helps.
Yes. Figure 4b shows that doing this further improves calibration. The overall Breyer score decreases as you average more confidence estimates. It makes the final confidence score more reliable, more robust.
That's clever. A pretty lightweight way to get more trustworthy confidence without needing whole new models. Just get more opinions from the same model about its own answer.
Precisely.
This brings up a really interesting question for me, something we touched on earlier. Does the reasoning process itself actually improve calibration? Or is it just about having that final confidence tag slapped on?
Yeah, is it thinking out loud about uncertainty just window dressing? Or does it genuinely help the model calibrate better?
Right. Did they investigate that?
They did. They ran a very cool experiment. They compared two types of classifiers trained to predict correctness. One was a baseline classifier, trained on the outputs of the standard RLVR model, which, remember, doesn't have any uncertainty reasoning in its output.
Okay, just predicts based on the answer itself.
Right. The other was an analysis classifier. This one was trained on the outputs of the RLCR model, so it saw the reasoning chains that included uncertainty analysis. But crucially, they removed the final confidence tags from the input for this classifier.
Ah, so the classifier saw the uncertainty reasoning, but not the model's explicit confidence number. It had to infer confidence from the reasoning itself.
Exactly. The question was, does seeing that reasoning help the classifier predict correctness better than just seeing the raw answer?
And what was the result? This feels important.
It was really telling, especially when looking at different model sizes. For the smaller models, they tested like 0.5 billion and 1.5 billion parameters. The analysis classifier, the one that saw the reasoning, significantly outperformed the baseline classifier.
Wow. So for smaller models, seeing the uncertainty chain of thought is essential for better calibration, even without the final tag.
That's the strong suggestion, yes. It implies that for models with more limited capacity, the explicit process of articulating uncertainty provides crucial signals that help in assessing the actual likelihood of being correct.
But what about larger models?
For the larger 7b model, the gap was much smaller. The bigger model seemed better able to infer the likelihood of correctness even without seeing the explicit uncertainty reasoning.
So maybe bigger models internalize this better, but for smaller, more resource-constrained models, that explicit reasoning about uncertainty makes a really significant difference for calibration.
That seems to be the key insight from Figure 5. The internal thought process, the articulation, creates more robust signals, especially when the model's capacity is limited.
It's like showing your work in math class, it helps you, and the grader understand your confidence.
That's a great analogy, yeah.
Okay, one last area the paper looked at was the self-consistency of the confidence estimates from RLCR. What does that mean?
They looked at consistency in two ways. First, intra-solution coherence.
Intra-solution.
Meaning, if the model generates multiple different uncertainty reasoning chains for the same single answer, or the confidence estimates it produces roughly the same. Ideally, they should be.
You don't want it saying 90% confident one time and 10% the next for the same answer.
Exactly. And Figure 6a in the paper shows that RLCR models generally have low variability here. The confidence estimates for the same answer tend to be quite consistent. That's a good sign.
Okay, consistent for the same answer. What's the second type of consistency?
Inter-solution consistency. This applies to tasks where there are multiple possible answers, but they are mutually exclusive. Only one can be right, like a multiple choice question.
Right. If A is the answer, B, C, and D must be wrong.
Exactly. So ideally, if the model is perfectly calibrated, the confidence scores it assigns across all possible answers, A, B, C, D, should sum up to 1 or 100%. It represents a coherent belief distribution.
Does RLCR achieve that? Do the probabilities add up?
Figure 6b shows the results. For in-domain data, RLCR's confidence sums cluster pretty tightly around 1, much better than RLVR. It indicates a reasonably well-calibrated overall belief distribution on familiar territory.
That's impressive. What about out of domain?
Overconfidence does still remain for O tasks, as we saw with the ECE scores earlier. The thumbs are often greater than 1. However, the paper notes that RLCR is still significantly closer to the ideal sum of 1 compared to RLVR, even ODE.
So, not perfect consistency on new tasks, but a definite improvement towards having a more coherent set of beliefs, even when facing the unknown.
A huge step in the right direction, yes.
Okay, so let's try and wrap this all up. To recap, this RLCR method seems like a genuinely significant step forward in how we train large language models.
I think so.
By incorporating these proper scoring rules, like the Breyer score, directly into the reinforcement learning process.
Instead of just that simple right-wrong signal.
Right. Models can now simultaneously improve both their accuracy and, crucially, their calibration, their ability to know what they know.
And know what they don't know, which is just as important, if not more so in many cases. They get much better at assessing their own uncertainty.
And this isn't just about getting better scores on a leaderboard, you see. It's really about building AI systems that are more reliable, more trustworthy.
Exactly. Systems that can operate more responsibly in those sensitive domains we talked about: healthcare, law, finance. Anywhere you need nuance.
Providing us with valuable, nuanced information, not just answers that sound confident but might be completely off base. For you, the listener, this points towards AI tools in the future that you can depend on more.
Whether it's for research, solving problems, or just getting accurate information online, having a better sense of the AI's confidence is invaluable.
Absolutely. And that leaves us with, I think, a really compelling final thought for you to mull over. While RLCR clearly makes incredible strides forward, especially on generalization and that self-consistency,
It's a big leap.
it is. But the research paper itself is honest. It points out that, quote, even after RLCR, out-of-domain calibration error is often high in an absolute sense.
Still room for improvement, definitely.
And models may still assign high confidence to multiple contradictory answers in some ODE cases. So this leaves us with a fascinating question, really. If LLMs are truly learning to be more honest about their uncertainty, how much further can we actually push this self-awareness?
That's the frontier.
What new applications become possible if we can genuinely, truly trust in AI's confidence levels? And maybe more fundamentally, what will it actually take for these systems to achieve near-perfect calibration, even when they face completely novel, maybe even unprecedented situations?
That's a challenging question, and probably involves more than just better training methods. But it's the direction we need to be heading, a critical area for future work.
Definitely something to think about. That's all for this deep dive.